Alright, so this is our AP Chemistry Chapter 9 lesson video part 3, and in this one we only have section 9.6 left to do. So we talked about hybridization, we've been talking about VSEPR, and so now we're going to kind of put it all together. So multiple bonds. A sigma bond is a bond that occurs when a line that passes through the two nuclei of the bonded atoms also passes through the middle of the orbital overlap. So all that means is that's a really wordy way of saying, here's our two nuclei. You can see that shaded region, that's the overlap. If I draw a line between the two nuclei, it's going to pass through that overlap. The same thing happens if I have an S and a P. See, I can draw a line between the two. It passes through the overlap. And the same thing happens sometimes when two P's overlap, if they overlap in this orientation. I'll show you what it looks like when they're not in this orientation. So if you can draw a line and it passes through the overlap, that's referred to as a sigma bond. A pi bond, on the other hand, occurs when the overlap of the orbitals is perpendicular to the internuclear axis. In a pi bond, the overlap occurs above and below the nuclear axis. So see, these were the examples we just saw on the previous slide. But see, two p orbitals could overlap like this. Now I know this picture is kind of small. So here I'll just kind of draw an example right here. So our p's could overlap right here and here. So see how if I draw a line between them, they don't pass through those overlaps? That's referred to as a pi bond. It can also happen between a P and a D. Remember, the D looks like the four-leaf clover. Or it can happen when two D orbitals overlap. It just depends on the orientation. So that's how you know if something's sigma or pi. Unlike a sigma bond, in a pi bond, there is no probability of finding the electron on the internuclear axis. So like if this was a sigma bond, there is high probability the electron is going to be right there on that internuclear axis, which is just a line between the two nuclei. Whereas if these p's are overlapping, there's no chance the electrons can be on that internuclear axis. So since the p orbitals in a pi bond have overlap sideways rather than directly facing each other, the total overlap in a pi bond tends to be less than in a sigma bond. This means that pi bonds tend to be weaker than sigma bonds. So sigma bonds can usually just get more of an overlap than a pi bond can. Single bonds are sigma bonds, so that's an easy way to know if it's sigma or pi. A double bond consists of one sigma and one pi. Okay, and so what happens is, I know this picture is kind of hard to understand, you have a sigma overlap right here, and then the pi overlap right here. And I know it seems like, oh, well, this is a triple bond. This is all one orbital. Remember, the p's have the two lobes, okay? That's still only one p orbital. All right, and so that's what a double bond would look like. And so then a triple bond, on the other hand, is one sigma and then two pi's. So you have your sigma overlap like this, and then your other two p orbitals will overlap like that. So since pi bonds occur using unhybridized p orbitals, it can only occur with sp and sp2 hybridization. Okay, so in summary, a single bond is a sigma bond, double is one sigma, one pi, triple is one sigma, two pi. So super easy way to tell. So it says formaldehyde has the Lewis structure, this right here. Describe how the bonds in formaldehyde are formed in terms of overlap of appropriate hybridized and unhybridized orbitals. Okay, so I can look around C and tell that there are three domains. So I know that this hybridization around C is sp2, because there's three domains. So 1, 2, 3 means there's hybridization sp2. All right. I can tell that between the C and the H, it's a sigma bond. So my CH is a sigma bond. I know that it's being formed by the 1s orbital of H, and it's being formed with a hybridized sp2 orbital for C. Okay, so it's a hybrid sp2 orbital with the C. That's what's overlapping. And then I know over here for O, again, I can see three domains. So O also has sp2 hybridization around itself. All right. right, and so then I can see that there is a sigma bond between CO and there is a pi bond in between CO. All right, because double bonds are 1 sigma and 1 pi. I put an extremely long answer, so hopefully all of my little shorthand up here answered everything I wrote down here. So I wrote both H atoms would be bonded to C with unhybridized 1s orbitals making sigma bonds. Okay, we did write that part. Okay, but I'm going to have to click because I just went on this one. So then I wrote the C has a trigonal planar electron domain geometry, so it has sp2 hybridization. Okay, said that. So 3 sp2 hybrid orbitals make the 3 sigma bonds. The remaining, so this part I didn't say this in all my little chicken scratch a second ago. The remaining unhybridized 2p orbitals will form that pi bond with oxygen. Oxygen's also trigonal planar and has sp2 hybridization. So one sp2 orbital forms the sigma bond with carbon. The other ones have the lone pairs, and then that unhybridized 2p orbital forms the pi bond. Okay, so the only part I left out of all of this was the unhybridized 2p orbitals for the C and the O to form that pi bond. Alright, so thankfully you got one that's a little bit shorter. So y'all try this one, pause it. It looks like there's maybe parts on the next slide too, so y'all go ahead and try this. I'll assume you've done that. So let's look at it together. So part A says predict the bond angles around each carbon atom. Okay, so I'm just going to call this carbon 1 and carbon 2, so that way I can denote which one I'm talking about. Okay, so as much as it appears that this is a 90-degree angle, remember you have to think in 3D form. This carbon has 4 domains. That's tetrahedral. And so we know that tetrahedral has a bond angle of 109.5 degrees. This carbon right here has 2 domains. That is literally as far apart as they can get. So this carbon would have 180 degrees. So see, sometimes when it's the flat shape, the bond angle is correct, like on 180. But sometimes it's not, and that's a super common mistake, is people will see this and get all excited because they're like, oh, that's a right angle, that's 90 degrees. Okay, but remember, this is 3D we're talking about here. So hopefully you got that right. So then it says, describe the hybridization at each carbon atom. Okay, so here, I'm going to come back here. So again, I'll call this C1 and C2. So C1's hybridization, there's 4 domains, so SPPP, or SP3. All right, around C2, remember, a triple bond is still only 1 domain. So there's 2 domains, so it's just SP. Okay, because 2 domains, S and P. Just like that. So hopefully you got that one right. Okay, and then let's look at part C. So it says, determine the number of sigma and pi bonds in the molecule. So super easy. So sigma is all single bonds and one of a multiple bond. So I have 1, 2, 3, 4, 5 sigma bonds because it's all my single bonds and one of a multiple bond. Pi bonds are the others of a multiple bond. So one of them sigma, so 2 of them are pi, just like that. Okay, so hopefully you got that right and thought that was pretty easy. Alright, so last thing we have to talk about is localized and delocalized electrons. So localized electrons belong to the 2 atoms that form the bond. So they are going to stay in that domain area and not go anywhere else. Well, when you have resonance structures that exist for a molecule, the electrons move around and then they're called delocalized. So think about when we talked about benzene. Remember, benzene was C6H6, and so it has alternating single and double bonds, but then they can change. And remember, we talked about instead of the bond order being 1 or 2, it's a 1.5. So those are called delocalized electrons. So the way you know if electrons are delocalized is whether or not you have resonance. So it says, describe the bonding in the nitrate ion, NO3 negative. Does this ion have delocalized pi bonding? Okay, so first thing I would need to do is draw it. So N has 5 valence electrons, O has 6 times 3, and the -1 means plus 1 more. So I have 18 plus 5, which is 23, plus 1 more, which is 24 valence electrons. All right, so I'll put my N in the middle, put my 3 O's around it. O has 2, so it needs 6 more for each of them. And then N has 2, 4, 6, so it needs 2 more, just like that. All right, but the problem is I'm only allowed 24. I actually have 26. So I need to add an extra bond, remove a pair from both of the atoms that touch that bond, and so now I can determine if I have localized or delocalized pi bonding. So I could put my double bond here, here, or here, which means I do have resonance, and I'm just going to go ahead and put the negative in the brackets just to make sure it's correct. So I do have resonance. I'm not going to draw all three of them. But once I realize I have resonance, that's when I realize I do have delocalized pi bonding. Okay, because we have those electrons that are able to move between the electron domains. All right? So like I said, you just got to draw it to know. Okay? Oh, whoops, I put way more than that in my answer. So N is trigonoplanar, so it is sp2. That extra p orbital makes a pi bond in the double bond, and the pi bond is delocalized since resonance structures exist. Okay, so I went a little more in depth into my explanation here. All right, so y'all tried this one. It says, which of the following molecules or ions will exhibit delocalized bonding? So all you need to do is figure out resonance, yes or no. If there's resonance, it's delocalized bonding. All right, so we got to draw all, 5 of them. Okay, so we have SO3. So here, I'll just start a little list over here. SO3, so S has 6, O has 6 times 3, which is 18, plus 6, which is 24 valence electrons. So S goes in the middle, and since I have to do so many of them, 1, I'm going to go incredibly fast. 2, I'm not going to actually draw any resonance. We'll just point out if we have resonance. All right, so I'm going to make all my oxygens have an octet and sulfur. The problem is I have 26. I'm only allowed 24. I will have to do a multiple bond, remove a pair off of each. So once I know that, and I know that multiple bond can go in any location, this one does have delocalized bonding. So SO3 is a yes, it does. All right, so let's move on to SO3 negative 2. So S has 6, O has 6 times 3, plus 2 more. That's going to give me 26 valence electrons. So once I put all my oxygens around it and give them all an octet, S has 2, 4, 6, so it needs 2 more. But this time I'm allowed to have 26. So I don't have to put a double bond anywhere, so I have no resonance, so this one would not have delocalized bonding. All right, so I move on to H2CO. So H has 1 times 2, C has 4, O has 6, for a total of 12 valence electrons. Let me double check my total. If you watched my previous video, remember I made a mistake. All right, so I put my C in the middle. I'm going to bond my O and my H's. Okay, so H has 2, so it's good to go. O needs 6, and C needs 2, 4, 6, so it needs 2. The problem is I'm allowed 12, 2, 4, 6, 8, 10, 12, 14, so I am going to need a multiple bond. But in this case, even though there's a multiple bond, you may be quick to say, oh yeah, that has delocalized bonding. But are you able to put a multiple bond to a hydrogen? No, hydrogens can only accept a duet. So even though I have a multiple bond now, there is still no resonance because, of course, it can't move to hydrogen. Oh, and also keep in mind, y'all, I'm not drawing the correct 3D shape. I'm just drawing the flat shape for these. Okay, so this is a no, even though it does have a multiple bond. All right, so next is O3. So O has 6 times 3, which is 18 valence electrons. All right, so tic-tac-toe, 3 in a row. O has 2, so it needs 6. O has 2, so it needs 6. O has 4, so it needs 4. I'm allowed 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I am going to need a multiple bond, remove a pair off of each. And so in this case, could the multiple bond be on the other side? It sure could. I have resonance, so O3 would experience delocalized pi bonding. All right, and then last one is NH4 positive. Woo, I'm running out of room. So N has 5, H has 1 times 4. Positive means we're going to subtract an electron. Okay, so I have 9 minus 1, which is 8 valence electrons. So I put my N in the middle, spread all my H's out. And again, y'all, even though since I'm drawing the flat one, even though this looks like they're at a 90-degree angle, remember this is really tetrahedral, so it's really 1 and 9.5. So all my H's are stable with 2, my N is stable with 8, and then I have 8 total. So I'll put my brackets and my charge. And so there is no resonance for this, so this one would not have any kind of delocalized bonding. All right, so your answers for this one should have just been SO3 and O3. So hopefully you got that one right. And to see, a question like this would take an extremely long time on the AP exam if you are not really fast at being able to draw those Lewis dot structures. Okay, you don't want to waste time doing something like that. All right, so moving on to our sample integrative exercise. Oh, we're almost done. So it says elemental sulfur is a yellow solid that consists of S8 molecules. The structure of the S8 molecule is an 8-membered ring. Heating elemental sulfur to high temperatures produces gaseous S2 molecules. So we have S8 solid. When we heat it, it becomes 4 S2 gas molecules. With respect to electronic structure, which element in the second row of the periodic table is most similar to sulfur? So we know elements in the same group are similar. So if I'm in the second row or second period, I would want to go to the element that's right above sulfur. So in that case, it would be oxygen. Okay? Because they're in the same group. We just want them to be in the same group. All right, then it says use the Vesper model to predict the SSS bond angles in S8 and the hybridization at S in S8. So we need the bond angle and hybridization. So let's draw this thing. All right, so S has 6 valence electrons, and there are 8 of them, so that's 48 valence electrons we have to work with. So they told us it is an 8-membered ring. So we just kind of, whoops, for some reason I keep trying to write C's. It's because in organic, you do a lot of C rings. All right, so we've got our 8-membered rings, because that's what it told me. So right now, every S has 4. So I just need to add 2 lone pairs to each S. And then if you count up, like I'm not going to make you watch me count, it is 48. Okay, like you can just count on your own. All right, so it says predict the bond angles. Well, I can look at an S and see there are 4 domains. So that means I need to think, hey, that's similar to tetrahedral. So if there's 4 domains and it's tetrahedral, your bond angle will be about 109.5. Okay, then it says what's the hybridization around each S. And you could on this one say, you know, hey, wait a minute, there's 2 lone pairs. You could put less than 109.5 if you wanted. Really, maybe just put approximately 109.5. But when we talk about hybridization, again, there are 4 domains. 4 domains means 4 hybrids. S, P, P, P. So the hybridization would be sp3. Just like that. Okay, so that's all you got to do. All right, so let's move on. Almost done. All right. So then, okay, I skipped C for some reason, so we must not do that. So we're skipping on to D. So it says use average bond enthalpies from table 8.4 to estimate the enthalpy change for the reaction just described. Is the reaction exothermic or endothermic? Okay, so our reaction is this right here. S8 yields 4 S2 gas. Okay, so we have S8 solid yields 4 S2 gas. All right, so we got to look at bonds broken minus bonds formed, because remember, that's our bond enthalpy. It's bonds broken minus bonds formed. All right, so we already drew this. So here, let me see if I have a picture of it so we don't have to draw it again. So it's right here. Okay, we already drew this, so I can see there's 1, 2, 3, 4, 5, 6, 7, 8 SS bonds. Okay, so I'm not going to sit there and redraw that. So there's 8 SS bonds right here. Okay, so when I do my bonds broken, it's going to be 8 SS single bonds. And then minus my bonds formed. So first of all, I got to figure out what S2 looks like then. Is that like a single bond? Is it a double bond? Is it a triple bond? So S has 6 times 2, which is 12. So I do my S and my S. Each one needs an octet, so I do like this. Well, I'm allowed 12, 2, 4, 6, 8, 10, 12, 14. So I will need a multiple bond there. So I do need to know that's what it looks like. So I'm actually forming 4 SS double bonds. Because remember, we have to take into account these coefficients. So I'm going to minus 4 SS double bonds. So then I would go to my bond enthalpy chart to get the numbers. So I have those written down right here. So it ends up being 8 times for that SS single bond, it's 266. Remember, that's kilojoules per mole. And then 4 times SS double bond is 418. And so I end up getting 456 kilojoules. So since my delta H is positive, that makes it endothermic. Okay, if my delta H was negative, that would be an exothermic reaction. So it's endothermic. All right, and I like these sample integrative exercises because they keep kind of going back and forth between different chapters, kind of like an actual free response question. All right, and so that is the end. So the only new thing really from this chapter was talking about that potential energy internuclear distance curve, doing the bond enthalpy. We didn't do that in honors, and then just some of the other areas we might have gone a little more in depth than we did in honors. But hopefully, like I said, for this chapter, mainly it was a refresher of Vespers.